What if everything, every star, every galaxy, every atom in your body came from nothing? Not just empty space, but absolute nothingness. No matter, no energy, no time. And yet here we are, in a universe bursting with complexity, stretching for billions of light years in all directions. How does something emerge from nothing? Has the universe always existed in some form? For decades, scientists have tried to piece this puzzle together. Was our universe born from a quantum fluctuation? Did an earlier cosmos collapse and explode into a new cycle of existence? Let's dive into the strangest, most mind-bending theories of the universe's origins. If you think the Big Bang is the final answer, think again. The truth might be far weirder than you imagined. Historical shifts, from classical void to quantum vacuum. What once seemed like an empty void, a vast nothingness, has become something far more complex. From ancient times to modern physics, our understanding of empty space has undergone a complete transformation. What was once thought to be a featureless emptiness is now known to be teeming with activity at the smallest scales. This shift didn't happen overnight. It was the result of centuries of observation, debate, and discovery. In ancient Greece, philosophers like Aristotle rejected the idea that true emptiness could exist. To him, nature abhorred a vacuum. He believed space must always be filled with something, whether air, fire, or some other invisible substance. This idea dominated scientific thought for centuries. Even as new theories emerged, the belief in a medium that filled space remained strong. The 17th century brought a turning point. The work of Galileo and later Newton helped shape a new understanding of space. Newton described space as an absolute void, a background in which objects moved according to predictable laws. To him, space itself had no structure. It was simply a stage on which the universe played out. This idea of empty space as a passive void became widely accepted. However, even in Newton's time, some scientists suspected that space might not be entirely empty. During the 19th century, scientists proposed the existence of an invisible medium called the ether. This ether was thought to fill all of space and serve as the carrier of light waves. Since sound needed air to travel, scientists assumed light also needed a medium. The idea of the ether fit well with Newtonian physics. However, in the late 1800s, a famous experiment changed everything. The Michelson-Morley experiment attempted to detect the motion of the ether by measuring how light moved through space. The results showed no sign of the ether's existence. This was a major problem for physics. If space wasn't filled with ether, what was it? At the turn of the 20th century, Einstein's theory of relativity provided a new way to think about space. Space was not an empty void, but a dynamic fabric that could stretch and bend. Gravity was no longer seen as a force pulling objects together. Instead, it was the result of massive objects warping the structure of space itself. Einstein's view of space as something that could be shaped and influenced was a step away from the old idea of an absolute void. Still, it wasn't yet clear just how active empty space could be. The most dramatic shift came with the rise of quantum mechanics, which showed that even in a vacuum, particles could pop in and out of existence. These were called virtual particles, appearing and disappearing so quickly that they couldn't be directly observed. This constant activity gave rise to what became known as the quantum vacuum. Instead of a passive void, space was filled with fluctuations, tiny bursts of energy happening everywhere, all the time. This discovery changed everything. The vacuum was no longer just an absence of matter. It was an active participant in the universe. The effects of these fluctuations could even be measured. The Casimir effect, first proposed in 1948, showed that two closely placed metal plates could experience an attractive force due to the quantum vacuum. This was solid evidence that the vacuum had real physical properties. In quantum field theory, every type of particle has a corresponding field spread throughout space. Even when no particles are present, these fields continue to exist, constantly fluctuating. The Higgs field, for example, gives particles their mass. Without it, the fundamental particles that make up matter wouldn't exist in their familiar form. This new understanding of empty space reshaped cosmology as well. The discovery of dark energy, the mysterious force causing the universe's expansion to accelerate, is closely linked to the quantum vacuum. Some scientists believe that vacuum energy, arising from quantum fluctuations, may be responsible for this cosmic acceleration. However, the exact nature of dark energy remains one of the biggest mysteries in physics. The journey from the classical void to the quantum vacuum has been a major shift in scientific history. What was once thought to be nothing is now seen as a source of energy and activity. Even now, the study of the quantum vacuum is far from complete. Scientists are still exploring its role in the universe. Could vacuum energy be harnessed? Could new physics be hiding in the structure of empty space? The answers to these questions will continue to reshape our understanding of the cosmos. Quantum fluctuations, the spark in the void. In classical physics, a vacuum is simply an absence of matter. But in quantum physics, even empty space contains energy. This energy appears in the form of short-lived virtual particles that briefly exist before disappearing again. These particles don't behave like normal matter. Instead of existing in a stable state, they emerge and vanish so quickly that they can't be directly observed. However, their effects can be measured, proving that they are real. The Big Bang, which started everything, is often described as a massive explosion. But what triggered it? One possibility is that a quantum fluctuation, arising from an unstable state of empty space, set the process in motion. At an incredibly small scale, the universe may have begun as a tiny fluctuation in a quantum vacuum. Normally, these fluctuations are brief, appearing and disappearing almost instantly. But under certain conditions, a fluctuation could become stable and expand rapidly. This idea is closely tied to inflation, the theory that the early universe expanded at an extraordinary rate. Inflation suggests that, in a fraction of a second, the universe grew from an unimaginably small size to something vast. If a quantum fluctuation triggered this expansion, it would mean that the universe itself emerged from the energy present in the vacuum. Instead of starting from a singular explosion, the cosmos could have begun as a sudden stretching of space, driven by the hidden energy of empty space itself. If a quantum fluctuation could create one universe, could it create more? Some scientists believe that fluctuations like this might happen all the time, producing countless universes beyond our own. This idea, known as eternal inflation, suggests that new regions of space could constantly be forming in an ever-expanding cosmic landscape. Even within our own universe, quantum fluctuations left their mark. As inflation stretched space, tiny fluctuations were magnified. These small differences in energy density later became the seeds of galaxies and stars. Without them, matter might have remained evenly spread, and no structures would have formed. The galaxies we see today may owe their existence to random quantum events that happened in the first fractions of a second after the Big Bang. The idea that the universe could emerge from nothing may seem strange. However, experiments confirm that quantum fluctuations are real and have measurable effects. In particle physics, fluctuations play a role in the behavior of fundamental forces and particles. If quantum fluctuations shape the universe on a small scale, it's possible they influenced it on the largest scale as well. The vacuum also isn't just a backdrop for particles. It has energy of its own. In some theories, this vacuum energy could shift from one state to another, causing massive changes in the universe. If an unstable vacuum state existed before the Big Bang, a quantum fluctuation could have triggered a transition, leading to the birth of the cosmos. If a quantum event started the universe, does that mean other universes could be forming right now in other parts of reality? Could new universes emerge in the distant future? These possibilities follow naturally from the strange rules of quantum physics. Beyond the Bang, pre-Big Bang hypotheses. The Big Bang is the foundation of modern cosmology, the event that marks the start of the observable universe. But what if it wasn't the true beginning? For decades, physicists and cosmologists have examined the possibility that the universe had a history before the Big Bang. Some theories suggest that the cosmos has gone through endless cycles of expansion and contraction, never truly beginning or ending. Others propose that our universe was born from a much larger, pre-existing reality, possibly as a result of interactions between hidden dimensions or unknown physical forces. If any of these ideas are correct, the Big Bang was not the beginning, but just one event in a much larger and older cosmic story. One of the most discussed alternatives to the idea of a single beginning is the cyclic universe model. This concept suggests that the universe follows a repeating pattern, expanding, slowing down, contracting, and then starting over again. Instead of a single Big Bang, followed by endless expansion, the cosmos could go through an infinite series of Big Bangs and Big Crunches. Ancient cultures, including Hindu and Buddhist traditions, imagined the universe as undergoing endless cycles of creation and destruction. In modern physics, this concept has been explored in various forms. Some versions propose that dark energy might one day reverse, pulling everything back together. The universe would shrink down to an incredibly dense state before bouncing back in another explosion. This process, repeated infinitely, could mean that the universe has no true beginning or end, only endless rebirth. A variation of this idea is the Big Bounce theory. It suggests that rather than collapsing into a singularity, a previous universe reached a highly compressed state and then rebounded, creating our current expanding universe. In classical physics, gravity would eventually pull everything back into a single point, creating a singularity. But in quantum mechanics, effects at the smallest scales could prevent this total collapse. Instead of a singularity, a new expansion could begin, leading to a fresh universe. Some versions of this theory suggest that each new universe might carry imprints from the previous one, tiny differences that could be reflected in the cosmic microwave background. String theory proposes that the fundamental building blocks of reality are tiny vibrating strings, rather than point-like particles. In one version of string theory called the ekpyrotic model, the universe was formed not by a singular explosion, but by a collision between two enormous higher dimensional surfaces known as branes. According to this idea, space could have more than the 3 dimensions we experience, and these higher dimensional structures could interact in ways that create entire universes. In that case, the Big Bang would not be a unique event. It would be just one of many such collisions occurring across an unimaginably vast cosmic landscape. Another possibility is that the universe emerged from quantum fluctuations in an eternal vacuum. If a fluctuation occurred under the right conditions, it could have triggered rapid inflation, leading to the birth of our universe. This idea suggests that the universe is just one bubble in a much larger quantum reality, constantly giving rise to new universes, which leads to the idea of the multiverse, a vast collection of universes, each with its own unique properties. Some versions of the multiverse theory propose that every quantum event spawns a new universe, creating an endless number of parallel realities. Others suggest that different regions of space are constantly producing new universes, separated from one another by immense distances or even by different dimensions. If true, this would mean that our universe is just one of countless others, each with its own physical laws, matter, and possibilities. Some theories suggest that instead of starting at a single moment, time could stretch infinitely into the past. In this view, what we see as the Big Bang might simply be a transition from one phase of existence to another. One way to explore these ideas is through mathematical models and observations of the cosmic microwave background radiation, or CMB. This faint glow, left over from the early universe, carries clues about what happened in the first moments after the Big Bang. Some scientists believe that subtle patterns in this radiation could reveal hints about a pre-existing universe. If traces of an earlier phase of the cosmos were found, it would be a major breakthrough in our understanding of cosmic history. Since the laws of physics as we know them break down at the extreme conditions of the early universe, it is difficult to gather direct evidence about anything that might have come before. Many of these ideas, while based on solid theoretical foundations, remain speculative because they cannot yet be tested. However, advances in physics and technology may one day provide new insights. As scientists develop more precise instruments and explore deeper questions about the nature of space, time, and matter, they may uncover clues that point to a time before the Big Bang. Quantum gravity's role in cosmic genesis. The universe follows two sets of rules that seem completely different. One set governs how planets, stars, and galaxies behave, following the familiar laws of gravity first described by Isaac Newton and later expanded by Albert Einstein. The other set governs the strange world of the very small, atoms, particles, and the energy fields that surround them, described by quantum mechanics. Both theories have been tested and confirmed in countless experiments, yet they seem impossible to combine. This is a major problem because to truly understand the birth of the universe, both gravity and quantum mechanics must be considered together. At the moment of the Big Bang, the entire universe was packed into an unimaginably small space. This means gravity was acting at the quantum scale, where the rules of quantum mechanics take over. But Einstein's theory of general relativity, which explains gravity on large scales, does not work at the quantum level. Similarly, quantum mechanics, which describes small-scale physics, does not include gravity. The two theories break down when combined, leaving physicists without a complete explanation for the earliest moments of the universe. To understand cosmic origins, scientists must develop a theory that merges these two fundamental forces into one unified framework. One approach to solving this mystery is the search for quantum gravity, a theory that explains how gravity works in the quantum world. This is considered one of the biggest unsolved problems in physics. If a theory of quantum gravity is found, it could reveal what happened in the first instant of the universe, possibly even before the Big Bang itself. One of the leading ideas in quantum gravity is string theory. Instead of treating particles as single points, string theory suggests that everything is made up of tiny vibrating strings. These strings are so small that they would be impossible to see, even with the most powerful microscope. Depending on how they vibrate, these strings could represent different forces and particles, including gravity. In this view, gravity is not a separate force, but an effect of these vibrating strings interacting with space. String theory also suggests that space may have more than 3 dimensions. While we experience height, width, and depth in our everyday world, extra dimensions could exist, hidden from view. If true, the early universe may have behaved very differently than we expect. These extra dimensions could have influenced how space expanded after the Big Bang, or even played a role in how the universe came into existence in the first place. A different approach to quantum gravity is loop quantum gravity. Instead of treating space as a smooth background, this theory suggests that space itself is made of tiny, indivisible units, much like pixels on a screen. These quantized bits of space create a structure that could prevent the universe from collapsing into a singularity. This could explain how the universe transitioned from a previous state into the one we see today. Some versions of loop quantum gravity suggest that time itself might be fundamentally different at the quantum level. Rather than flowing smoothly, time may emerge from deeper interactions within the fabric of space. This could mean that time existed before the Big Bang, allowing for a history that stretches back beyond the beginning we currently recognize. A third idea comes from the holographic principle. This concept suggests that the entire universe may be like a 3-dimensional projection of information stored on a distant, lower-dimensional surface. In this view, the universe's deepest structure is not made of physical matter, but of information itself. If the holographic principle is correct, the birth of the universe might not have been a traditional explosion, but rather the emergence of information forming space and time. One of the biggest challenges in developing a theory of quantum gravity is testing it. Unlike other areas of physics, where experiments can be done in labs or with telescopes, The conditions needed to study quantum gravity directly would require recreating the extreme environment of the early universe. Since that's impossible with current technology, physicists must look for indirect clues, subtle patterns in the CMB, the behavior of black holes, or strange effects in high-energy particle experiments. Black holes are similar in some ways to the conditions of the early universe. Stephen Hawking famously predicted that black holes slowly lose energy over time through a process now called Hawking radiation. This happens because quantum effects near the black hole's edge cause particles to pop into existence and escape. If quantum gravity plays a role in black holes, studying their evaporation could provide insights into the universe's first moments. The CMB holds information about the early universe, and small irregularities in it could reveal whether quantum gravity had an effect during the first fractions of a second. If patterns appear that don't fit with standard cosmology, they could point to new physics beyond Einstein's equations. There is also the question of whether the universe needed a beginning at all. Some theories of quantum gravity suggest that time itself may behave differently under extreme conditions. If time and space emerged from quantum interactions, then the Big Bang might not have been a singular event, but rather a transition from one state to another. The universe may have always existed in some form, with no absolute beginning, only changes in its structure over time. If scientists succeed in merging quantum mechanics and gravity into a single framework, it could lead to entirely new ways of thinking about space, time, and the universe's structure. It might even provide the foundation for new technologies or discoveries. Scientists push forward, driven by the need to understand the fundamental nature of everything that exists. Emergence of spacetime, when geometry is born. Before the birth of the universe as we know it, there may have been no space and no time, at least in the way we understand these things. The fabric of reality itself might not be fundamental. Instead, it may have emerged from deeper processes that have nothing to do with familiar ideas of space stretching infinitely or time flowing smoothly. One way to think about this is to compare space-time to temperature. Temperature feels like a basic property of the world, but in reality, it is just the collective motion of microscopic particles. If you zoom in far enough to the level of individual atoms, the idea of temperature disappears. It is not something that exists on its own, but something that emerges from the behavior of many smaller pieces interacting. Some physicists believe space and time might work the same way. On the smallest scales, they may not exist at all, instead appearing only when enough interactions take place to give them meaning. In the quantum world, particles do not always have fixed locations. Their positions can be uncertain, and sometimes they exist in multiple states at once. If space itself is something that emerges, then at the smallest scales, locations may not exist in a definite way. Reality could be made of interconnected relationships, with space forming only when enough connections stabilize. Some theories propose that the fundamental structure of reality is not based on space at all, but on networks of information. In these views, space is not a physical thing, but a way of organizing relationships between tiny building blocks. These networks behave in a way that, at large scales, creates the smooth geometry of space that we experience. Just as individual grains of sand can form a solid beach, individual pieces of information could form the structure of space-time. One model based on this idea is known as causal set theory. In this view, space-time is not a continuous fabric, but a collection of discrete elements, like dots connected by cause and effect relationships. Instead of existing as a background, space-time is built from these connections, appearing smooth only at large scales. If causal set theory is correct, then at the smallest levels, space does not exist in the way we normally think. It is not an empty container, but something that emerges when enough interactions occur. Another approach comes from loop quantum gravity. Just as energy comes in discrete packets called quanta, space may be divided into tiny, indivisible units known as loops. These loops form a kind of network that underlies the structure of space-time. At small scales, space is woven together like a fabric made of interlocking loops. This would mean that space itself has a smallest possible unit, beyond which the idea of distance no longer makes sense. If space is made up of fundamental units, then time might be as well. Some physicists propose that time is not a continuous flow, but a sequence of discrete events, like frames in a film. At the quantum level, there may be a fundamental tick of time. This idea is supported by certain interpretations of quantum mechanics, which suggest that time emerges from changes in quantum states rather than existing independently. One of the biggest implications of these ideas is that the Big Bang may not have been the beginning of space and time, but rather the moment when they emerged from a deeper, more fundamental reality. If space-time itself had to form, then there could have been a stage before the Big Bang where space did not exist in any recognizable form. Instead of a single explosive event, the universe may have transitioned from a timeless quantum state into the dynamic, expanding cosmos we see today. Scientists are searching for evidence of these ideas in various ways. If space formed from deeper processes, then small imprints might still be visible in the oldest light in the universe. The extreme warping of space and time by black holes could also reveal how space-time behaves when pushed to its limits. If space-time is something that emerges, rather than something that exists on its own, what lies beyond space-time? What deeper principles determine its structure? And if space and time are not fundamental, what does that mean for our understanding of existence itself? Multiverse narratives, multiple beginnings from nothing. The cosmos, rather than being a single expanding bubble, could be a vast multiverse filled with countless separate regions, each with its own laws, structures, and origins. If this is true, then instead of asking how everything began, we might have to ask how many different ways something can emerge from what we call nothing. According to eternal inflation, space itself is constantly expanding at an incredible rate in most regions, but in certain pockets, the rapid expansion slows down. These slower regions become bubble universes, each forming with its own unique properties. Our universe could be one of these bubbles, surrounded by an endless cosmic foam of other universes. If eternal inflation is correct, then new universes could be forming all the time. The process never stops. Each bubble universe emerges from a quantum fluctuation, a random energy shift in the vacuum of space. This means that rather than a single Big Bang event, the cosmos could be filled with countless Big Bangs, each creating a separate universe. Some of these universes might have similar physical laws to ours, while others could be completely unrecognizable, governed by different rules of physics that make them alien and strange. In string theory, the way the strings vibrate determines the properties of a universe, its particles, forces, and dimensions. But string theory predicts that there are an immense number of ways these strings could be arranged. Some estimates suggest there could be around 10 to the power of 500 possible configurations, each corresponding to a different universe with different physical properties. In some versions of the multiverse, universes can even branch off from one another. The many worlds interpretation of quantum mechanics suggests that every quantum event, every tiny, random change in a particle's state could cause the universe to split. If this interpretation is correct, then an uncountable number of parallel universes could exist, each representing a different version of reality. Every decision, every movement of an atom could lead to a separate world where things unfold differently. If black holes are gateways to new regions of space, then each black hole in our universe could potentially give rise to a new universe beyond its event horizon. This would mean that our own universe might have formed from the remains of a previous one, continuing a never-ending cycle of cosmic creation. While the multiverse remains a highly speculative idea, scientists continue searching for ways to test it. Some look for evidence in the CMB. Others search for signs of extra dimensions or variations in fundamental constants that could hint at a deeper underlying reality. Vacuum energy and the sea of possibility. Vacuum energy comes from the fundamental nature of quantum fields. Even in a space with no particles, these fields are never completely at rest. They continue to vibrate at a fundamental level, producing short-lived bursts of energy. These fluctuations are normally small, appearing and vanishing too quickly to have a noticeable effect. However, under the right conditions, they could play a much larger role, potentially giving rise to entire universes. The concept of vacuum energy also connects to one of the biggest puzzles in physics, the cosmological constant. When Albert Einstein developed his equations of general relativity, he included a term called the cosmological constant to describe the energy of empty space. At the time, it was thought to be a mathematical adjustment, but later discoveries revealed that vacuum energy is real and has an observable effect on the universe. Today, the cosmological constant is linked to dark energy. The amount of vacuum energy in the universe appears to be incredibly small compared to theoretical predictions. If the calculations based on quantum field theory were correct, the energy of empty space should be strong enough to tear apart galaxies instantly. Instead, the observed value is much weaker, suggesting either that we are missing a key part of the picture or that there is an unknown mechanism balancing vacuum energy at just the right level for our universe to exist. If vacuum energy plays a role in creating new universes, then different regions of the multiverse could have different values for this energy. Some universes might have a much stronger vacuum energy, causing space to expand so quickly that stars and galaxies never form. Others might have almost no vacuum energy, leading to a universe that collapses in on itself shortly after forming. The fact that our universe has a vacuum energy compatible with life could be a clue that many universes exist, each with different physical properties. If space itself contains energy, then in theory, it might be possible to extract or alter this energy. This idea appears in discussions about advanced propulsion systems, where the manipulation of vacuum energy could one day allow faster-than-light travel. While purely speculative, the possibility of tapping into the energy of empty space remains an intriguing subject of exploration. The effects of this energy can be seen in experiments, such as with the Casimir effect, demonstrating that vacuum energy is not just a theoretical concept, but something that can influence physical objects in measurable ways. If vacuum energy is the driving force behind cosmic creation, then the birth of universes may not require an external cause. Instead, the natural fluctuations of the vacuum could be enough to trigger the formation of entire cosmic structures. Entropy's paradox. Low entropy beginnings in a high entropy cosmos. Entropy is a fundamental part of how the universe works. It is the measure of disorder, and according to the second law of thermodynamics, entropy always increases over time. Left alone, systems tend to move from order to disorder. A shattered glass never reassembles itself, and a drop of ink in water spreads out rather than gathering back into a single spot. Yet, when we look at the early universe, we find something unexpected. It began in an incredibly low entropy state, highly ordered compared to what came after. If entropy naturally increases, why was the universe so ordered at the beginning? When the universe first emerged from the Big Bang, it was in a hot, dense state. Matter and energy were evenly spread, with only tiny variations. This seems like a simple and chaotic state, yet in terms of entropy, it was remarkably low. Over time, the universe expanded, cooled, and formed complex structures like galaxies, stars, and planets. Eventually, these structures will break down, and everything will drift towards a state of maximum entropy, where matter and energy are spread out so evenly that no useful work can be done. This final state, often called the heat death of the universe, represents ultimate disorder. The puzzle is why the universe started in a condition that allowed all of this structure to form. If high entropy is the natural end state, then why didn't the universe begin in a high entropy state from the start? Why was there order that gave rise to stars and galaxies, instead of an immediate collapse into randomness? One way to understand the problem is to think about gravity. In most systems, an increase in entropy means things become more spread out. But gravity behaves differently. When a cloud of gas collapses into a star, it seems to be getting more ordered rather than more disordered. This happens because gravity pulls matter together, forming dense structures. Yet, in doing so, it actually increases the overall entropy of the universe by releasing heat and radiation. The process of structure formation is not a decrease in entropy, but rather a redistribution of it. Some physicists propose that the universe's initial state wasn't just low entropy, but also highly specific. In order for space and time to emerge as we know them, the initial conditions had to be just right, almost as if the universe began in a state of special fine-tuning. This is sometimes referred to as the past hypothesis, the idea that the early universe was simply in a unique condition that set the stage for everything that followed. While inflation can explain why the universe appears so uniform on large scales, it doesn't fully answer why entropy started out so low. The deeper question remains, why did inflation itself occur in the first place, and why was its starting condition so special? In the cyclic model view, the Big Bang is just one stage of a much longer history. If the universe collapses and then expands again, the conditions at each new beginning might be reset in a way that keeps entropy low. However, this idea raises its own challenges, such as explaining how entropy resets with each cycle instead of building up indefinitely. If the multiverse exists, then perhaps we live in a universe that just happened to begin with low entropy. In this case, our universe is one of many possibilities, and we observe a low entropy beginning simply because we exist in a universe where conditions allowed complex structures like galaxies and life to form. If our universe had started with high entropy, it might have been too chaotic for stars and planets to develop, and observers like us would not be here to ask these questions. This entropy paradox is not just a puzzle about the past, it affects how we think about the future. As entropy continues to increase, the universe will eventually reach a state where no further work can be done, where stars burn out, black holes evaporate, and all matter is evenly spread across an expanding void. But if the universe can begin again, or if new regions of space can emerge from vacuum fluctuations, then perhaps entropy is not the final word. Instead, the cycle of order and disorder may continue, driven by even deeper processes. Revisiting cosmic inflation, beyond the standard picture, the expansion associated with cosmic inflations smoothed out irregularities, making the cosmos look the way it does today. The theory explains why the universe appears so uniform in all directions, and why distant regions of space have similar properties, even though they should never have been in contact with each other. Inflation also accounts for the absence of certain defects in spacetime. Early models of the Big Bang predicted that relics like magnetic monopoles, hypothetical particles with only one magnetic pole, should be common in the universe. Yet, none have been found. Inflation explains this by stretching space so much that any such relics would be extremely rare or pushed far beyond the observable universe. These successes have made inflation a widely accepted part of cosmology, but the theory is not without its challenges. One of the biggest issues is that inflation relies on an unknown force. The rapid expansion is thought to have been driven by a mysterious field, sometimes called the inflaton field, which has no known counterpart in the standard model of particle physics. Scientists do not yet know what this field was or what kind of energy it carried. While many models propose possible explanations, there is no direct evidence for the exact nature of the inflaton, making inflation a theory that works well in explaining observations, but lacks a clear physical foundation. There is also the problem of how inflation ended. According to the theory, the inflaton field eventually decayed, transferring its energy into the particles and radiation that would go on to form the universe. But the process by which this transition happened is still not fully understood. Some models suggest that inflation ended smoothly, while others propose that it may have triggered violent bursts of energy, creating high-density regions that influenced later cosmic structure. These questions have led to alternative models, such as the eternal inflation model and the bouncing universe model, which go beyond the standard picture of inflation. Another approach involves modifying gravity itself. Some theories suggest that what we interpret as inflation could be the result of an unknown aspect of gravity that only appears at extremely high energies. These models propose that the fabric of spacetime behaved differently in the earliest moments of the universe, making it naturally evolve into a smooth, uniform state without requiring an extra field like the inflaton. If this is true, then inflation may be an approximation of a deeper, more fundamental process. In certain models of string theory, inflation could be driven by the interactions between extra spatial dimensions, which are predicted by the theory but are too small to be observed directly. If these extra dimensions influence the early universe, they could provide an entirely new explanation for how inflation worked, or even suggest that something else entirely took its place. Observational evidence is crucial for distinguishing between these competing ideas. One of the strongest pieces of evidence for inflation comes from the CMB. Tiny variations in this radiation reveal patterns that match what inflation predicts. However, different models of inflation, and even some alternative theories, can produce similar patterns, making it difficult to determine which one is correct. Scientists are looking for additional clues that could confirm or challenge inflation. One major goal is detecting primordial gravitational waves, ripples in spacetime that could have been created by inflation. If found, these waves would provide strong support for the idea of a rapid expansion phase. Experiments like those using specialized telescopes to study the polarization of the CMB are searching for these signals. A confirmed detection would not only strengthen the case for inflation, but also help narrow down which version of the theory is correct. Another approach involves looking for signs of non-uniformity on the largest scales. While inflation is expected to have smoothed out the universe, some variations in structure could still be present, depending on the specific details of how inflation happened. If these variations were found, they could provide hints about the nature of the inflaton field, or even suggest that inflation worked differently than currently believed. Singularities reimagined. New mathematical approaches. A singularity represents a point of infinite density, where space and time seem to break down. The idea of a singularity appears in two major places in physics, at the center of black holes and at the very beginning of the universe. If we follow the expansion of the universe backward in time, we reach a point where all matter and energy were concentrated in a single location of infinite density. But infinities in physics are signs that something is wrong. They suggest that our understanding is incomplete, that our equations are missing something fundamental. For decades, physicists have worked to resolve this issue, using new mathematical methods to reimagine singularities in a way that makes sense. If our best description of gravity, Einstein's general relativity, leads to infinities, it means we need a new approach. One mathematical approach involves modifying the equations of general relativity. Some models introduce extra terms into Einstein's equations that prevent singularities from forming. These modifications can be thought of as corrections that appear when quantum effects are included. By doing so, physicists are searching for a way to describe the birth of the universe without requiring an infinite, impossible state. Another mathematical technique involves alternative geometries. In standard cosmology, spacetime is described using a particular type of geometry. But some researchers suggest that near a singularity, the geometry of spacetime may change following different mathematical rules. If spacetime behaves differently at extremely high energies, the idea of an infinite singularity may no longer be necessary. Instead, the beginning of the universe could be described as a transition from one geometric state to another. This approach is inspired by topology, a branch of mathematics that studies the properties of space that remain unchanged under continuous transformations. By applying new topological methods, physicists hope to uncover a more accurate description of the earliest moments of the cosmos. A different possibility involves the use of complex numbers and higher dimensional spaces. In standard physics, time is treated as a real number, flowing in one direction from past to future. But some researchers propose that time itself might behave differently near a singularity. Instead of breaking down, time could follow an alternative mathematical structure that prevents infinite density from forming. By rewriting the equations of cosmology to include additional dimensions or complex variables, physicists are exploring new ways to describe the beginning of the universe. Some physicists argue that singularities might not even exist in reality. Instead, they could be an artifact of our incomplete understanding of gravity. In many areas of physics, infinities appear when our equations break down, only to disappear when a better theory is developed. For example, early models of electromagnetism contained infinities that were later resolved through the development of quantum field theory. It is possible that singularities in cosmology are similar, a sign that our current description of gravity is incomplete rather than a true feature of the universe. If this is the case, a future theory of quantum gravity could eliminate singularities altogether, replacing them with a smooth, continuous picture of the universe's earliest moments. Testing these ideas is one of the greatest challenges in modern physics. The conditions near a singularity are impossible to reproduce in a laboratory, and direct observations are limited to the information available from cosmic radiation. However, future experiments and observations may provide indirect evidence that supports or refutes these models. Primordial black holes, ghosts of the early cosmos. In the first moments after the Big Bang, the cosmos was unimaginably hot and dense, filled with rapidly expanding energy and matter. Small variations in density, which would later form the seeds of galaxies, were present even then. If some regions were dense enough, the force of gravity might have been strong enough to crush them into black holes almost instantly. These would be primordial black holes, formed not from dying stars, but from the chaotic conditions of the universe's birth. Unlike typical black holes, which form millions or billions of years after the Big Bang, primordial black holes would have been there from the very beginning. Their sizes could vary widely, from tiny microscopic ones to enormous black holes, many times the mass of the Sun. The smallest ones might have evaporated over time due to Hawking radiation. Larger ones, however, could still be out there, scattered across the universe, influencing the formation of galaxies, stars, and even the structure of the cosmos itself. If primordial black holes exist, they could explain several cosmic mysteries. One possibility is that they might make up a portion of dark matter, the invisible substance that makes up most of the universe's mass but has never been directly detected. The most widely accepted idea is that dark matter consists of some yet undiscovered particle, possibly weakly interacting massive particles, WIMPs, or axions. However, decades of searching for these particles have come up empty. No experiments have detected dark matter directly, and observations have yet to confirm its exact properties. Since black holes do not emit light, they could be hiding in plain sight, affecting the motion of galaxies and galaxy clusters. Some researchers have proposed that a population of small ancient black holes could account for at least part of the missing mass in the universe. Black holes interact with gravity just like dark matter does. They could explain the additional gravitational effects seen in galaxies without requiring new unknown particles. If these black holes are spread throughout space, they would create the same invisible mass that astronomers currently attribute to dark matter. However, there are challenges to this idea. For one, black holes are not truly dark. While they do not emit light themselves, they can interact with normal matter in ways that should be detectable. Even small black holes can capture and pull in gas and dust, a process called accretion. As matter falls toward a black hole, it heats up and emits radiation. If a large number of primordial black holes were present, they could have produced too much radiation in the early universe, altering the CMB. Observations of the CMB have placed strong limits on how many primordial black holes could exist without contradicting known data. Some models suggest that primordial black holes could still contribute to dark matter, particularly if they exist in a range of masses, or if they behave in unexpected ways. For example, if they tend to cluster together rather than being evenly distributed, their effects might be harder to detect. Others have proposed that instead of individual black holes, dark matter could consist of black hole remnants, objects left over after tiny primordial black holes evaporate due to Hawking radiation. There is also the question of supermassive black holes, the enormous objects found at the centers of galaxies, including the Milky Way. These black holes are millions or even billions of times the mass of the Sun, but how they formed so early in cosmic history remains an open question. One possibility is that primordial black holes provided the seeds for their growth. If some of these ancient black holes were slightly larger than others, they might have grown rapidly, merging with nearby matter to form the massive objects seen today. Instead of forming from collapsing stars, the first black holes in the universe may have been present from the start. Because they do not emit light, they can only be observed through their gravitational effects. Some scientists look for their presence in gravitational lensing, a phenomenon where massive objects bend and magnify the light from distant stars. If a primordial black hole were to pass in front of a star, it could briefly make the star appear brighter due to this effect. By carefully studying such events, astronomers might be able to determine whether tiny, ancient black holes are scattered throughout the cosmos. Another method involves searching for signs of their evaporation. Some primordial black holes may be disappearing even now, releasing brief bursts of high-energy radiation as they vanish. Satellites and observatories designed to detect gamma rays could pick up the final signals of these tiny objects as they fade away. In certain models, these ancient objects could have unusual properties, behaving differently from the black holes formed from collapsing stars. They might contain exotic states of matter, or even be connected to other parts of the universe through hypothetical structures like wormholes. Some models suggest that their presence could have affected the formation of the first stars and galaxies, altering the distribution of matter across the cosmos. If large numbers of primordial black holes existed, their gravitational pull might have shaped the universe on both small and large scales, leaving imprints that scientists could still detect today. One of the biggest questions surrounding primordial black holes is whether they were actually created. While the idea is compelling, no direct evidence has yet confirmed their existence. Various experiments and observations have placed limits on how many of these objects could be present in the universe. If they were too abundant, their effects would be obvious, but if they are extremely rare, finding them becomes even more difficult. The search for primordial black holes is part of a larger effort to understand the first moments of cosmic history. These objects, if they exist, could bridge the gap between the physics of the Big Bang and the black holes seen throughout the cosmos today. Seeds of structure, primordial black holes and cosmic web formation. The structure of the universe today is not random. It follows an intricate pattern of galaxies, clusters and filaments that stretch across vast cosmic distances, forming what scientists call the cosmic web. This large-scale arrangement of matter traces its origins to the very beginning of the universe. The faint imprints left in the CMB reveal tiny variations in density, which later grew into the galaxies and galaxy clusters we see today. While traditional models attribute this growth to quantum fluctuations stretched during inflation, some theories suggest that primordial black holes may have played a key role in shaping the cosmic structure. If primordial black holes were present in significant numbers, they could have influenced how matter clumped together in the young universe. Normally, the slight differences in density in the early universe allowed gravity to gradually pull gas together, forming the first stars and galaxies over hundreds of millions of years. But if primordial black holes existed, they would have provided additional gravitational wells that could have accelerated this process. Instead of waiting for tiny density fluctuations to grow on their own, these black holes would have acted as seeds, drawing in gas and helping structure to form more quickly. In some models, these early black holes might have merged to create the supermassive black holes found at the centers of galaxies today. The origins of these enormous black holes remain one of astronomy's great mysteries. While the standard explanation suggests they grew from smaller black holes over time, primordial black holes offer an alternative possibility. Some of these central black holes may have existed since the early universe, skipping the slow process of accumulation entirely. The gravitational presence of primordial black holes could have also shaped the cosmic web. The cosmic web forms as matter collapses along invisible filaments of dark matter, eventually leading to the formation of galaxies where these filaments intersect. If primordial black holes were part of this early environment, their gravitational pull could have strengthened some filaments while preventing matter from accumulating in others, subtly altering the way the cosmic web developed. The LIGO and Virgo observatories have detected waves produced by the collision of black holes billions of light-years away. Some researchers speculate that at least some of these merging black holes could be primordial in origin, rather than the remnants of stars. If future detections reveal black holes with unusual properties, such as masses that do not fit with standard stellar evolution, this could provide indirect evidence that primordial black holes exist. The search continues, and future discoveries may finally reveal whether primordial black holes were the hidden architects of the cosmos. CMB anomalies, the cosmic microwave background, as a relic archive. The CMB is often described as the universe's oldest light. This ancient radiation carries an imprint of the universe as it existed nearly 14 billion years ago. While the CMB appears almost perfectly uniform, small variations in its temperature and density tell the story of how galaxies and large cosmic structures eventually formed. These fluctuations are well understood and align with what we expect based on the standard model of cosmology. However, there are certain features or anomalies that do not fit neatly into our current understanding. One of the most well-known anomalies is the cold spot, a region in the southern hemisphere of the sky where the temperature of the radiation is lower than expected. Discovered by the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed by the Planck satellite, this region is larger and colder than typical fluctuations found elsewhere in the CMB. Some scientists believe the cold spot could simply be a statistical coincidence, an unusually large but random fluctuation. However, others suggest that it could be the result of something far more intriguing. One idea is that the cold spot is linked to a vast structure in the universe called a supervoid. A supervoid is an immense region of space with fewer galaxies and less matter than the surrounding areas. If a supervoid exists along the line of sight between Earth and the cold spot, it could have affected the way CMB photons traveled through it. This effect, known as the integrated Sachs-Wolf effect, occurs when light from the CMB moves through a region of lower density, losing energy as space expands. While some studies have found evidence for a supervoid in the direction of the cold spot, it does not seem to be large enough to fully explain the anomaly, leaving room for other possibilities. A more exotic idea is that the cold spot could be evidence of a collision between our universe and another bubble universe in a larger multiverse. If our universe is just one of many forming in a vast cosmic landscape, interactions between different regions could leave behind detectable signatures in the CMB. Some theorists have suggested that a past collision with another universe could have altered the temperature distribution of the CMB in certain regions, potentially explaining the presence of the cold spot. Another puzzling anomaly is the so-called axis of evil, a term used to describe a strange alignment of temperature fluctuations across large portions of the sky. According to standard cosmology, variations in the CMB should be randomly distributed at all scales. However, data from WMAP and Planck have shown that the largest scale fluctuations appear to be aligned along a particular direction, rather than being randomly oriented. This alignment is difficult to explain using conventional physics. One possibility is that the observed alignment could be an artifact of our position in the universe. Some scientists have suggested that if the local cosmic environment is not perfectly uniform, it could introduce a bias in the way we measure the CMB, creating the illusion of an alignment. However, no clear mechanism has been found that could produce such a large-scale effect without contradicting other observations. Another possibility is that the alignment is a sign that the universe has a preferred direction, or anisotropy at the largest scales. If true, this would challenge one of the key assumptions of modern cosmology, the idea that the universe is the same in all directions on large scales. Some theoretical models propose that the universe could have been imprinted with a preferred direction due to physics at the time of the Big Bang, perhaps related to the way spacetime itself expanded during inflation. If this were the case, it could point to new insights about the nature of the universe's earliest moments. Beyond these specific anomalies, there are other unexpected features in the CMB that scientists continue to investigate. Some studies have suggested that there are differences in the statistical properties of the CMB on opposite sides of the sky, an asymmetry that is difficult to reconcile with the standard cosmological model. Others have explored the possibility of subtle imprints left by exotic cosmic structures, such as cosmic strings, hypothetical defects in space-time that could have formed in the early universe. Studying these anomalies is challenging because the CMB is incredibly faint, and small errors in data collection or analysis could potentially introduce patterns that do not actually exist. For this reason, researchers take great care in refining their measurements, using independent datasets and sophisticated statistical techniques to ensure that any observed anomalies are real. The Planck satellite, for example, provided the most precise maps of the CMB to date, confirming many earlier findings, but also raising new questions. Future missions, such as the proposed PICO, or Probe of Inflation and Cosmic Origins satellite, aim to provide even more detailed data that could shed light on these mysteries. Whether these strange patterns are statistical coincidences, observational artifacts, or hints of new physics, each new discovery in the CMB brings us one step closer to uncovering the deeper mysteries of the cosmos. Polarization patterns. Uncovering hidden signatures in the CMB. While temperature variations in the CMB have provided insight into the early universe's structure, an even more subtle property, polarization, offers a deeper layer of information. Polarization patterns in the CMB could hold the key to understanding some of the most fundamental questions in cosmology, including how the universe evolved, whether inflation truly occurred, and even what kind of forces shape the very fabric of spacetime. Light waves are said to be polarized when they have a preferred direction of vibration. On Earth, polarization is commonly observed in reflections off surfaces like water or glass, where light waves become aligned in a particular direction. Similarly, the CMB's polarization was imprinted long ago when the first atoms formed, allowing photons to travel freely through space without constant interaction with free electrons. This transition, known as recombination, left subtle polarization signatures in the CMB, frozen in place as the universe expanded. There are two main types of polarization in the CMB, E-mode and B-mode. E-mode polarization is easier to detect and was first observed in the early 2000s. It arises naturally from density variations in the early universe, revealing how matter was distributed when the CMB was first emitted. E-modes confirm and refine the temperature-based measurements of the CMB, giving us a more complete picture of the universe's infancy. B-mode polarization, however, is much more challenging to detect, yet it carries even more profound implications. It is thought to arise in two different ways, one from gravitational lensing and another from primordial gravitational waves. The latter is of particular interest because it could provide direct evidence for cosmic inflation. If inflation happened, it would have stretched tiny quantum fluctuations into vast cosmic structures, leaving behind a distinct pattern of B-mode polarization in the CMB. Detecting this signal would be one of the strongest confirmations of inflation and a major breakthrough in cosmology. In 2014, the BICEP-2 experiment, based at the South Pole, made headlines by announcing that it had detected B-mode polarization possibly linked to primordial gravitational waves. The excitement was immense, as this would have been the first direct evidence of inflation. However, follow-up studies revealed that much of the signal could be attributed to dust within our own galaxy, which also polarizes light in a way that mimics the expected B-mode pattern. Despite this setback, the hunt continues, with new experiments designed to separate true cosmological signals from foreground noise. Beyond inflation, CMB polarization studies offer insight into the large-scale structure of the universe. As CMB photons travel through space, their paths are bent by the gravitational pull of massive cosmic structures, a process known as weak gravitational lensing. This effect subtly alters the polarization of the CMB, creating a secondary source of B modes. By mapping these lensing effects, scientists can infer the distribution of both visible and dark matter throughout cosmic history. This technique provides an independent way to study dark matter. Dark energy may also leave its imprint on the CMB's polarization. Changes in the universe's expansion rate affect how gravitational lensing distorts the CMB, providing another tool for studying this enigmatic force. While dark energy remains one of the biggest mysteries in cosmology, improved polarization measurements may offer clues about its nature and evolution over time. The future of CMB polarization research lies in even more precise measurements. The upcoming LightBird satellite, led by the Japan Aerospace Exploration Agency, is specifically designed to target primordial B modes with unprecedented sensitivity. By observing the sky with minimal interference from Earth's atmosphere, LightBird hopes to detect the faint imprint of inflationary gravitational waves if they exist. Meanwhile, next-generation ground-based experiments will continue to refine our understanding, pushing the limits of what can be observed. The search for primordial B modes is about probing the very nature of space-time, understanding the role of gravity in the early universe, and uncovering clues about the fundamental laws that govern reality. The CMB, often described as a cosmic fossil, holds secrets that scientists are only beginning to unlock. Polarization patterns, though subtle and difficult to detect, may ultimately provide the most profound insights into the history and evolution of the cosmos. Temperature fluctuations, new data, and unexpected trends. One of the key aspects of temperature fluctuations in the CMB is their distribution across different scales. In theory, there should be a specific balance between large-scale and small-scale fluctuations, with smaller variations becoming increasingly prominent as one zooms in. This relationship follows a pattern predicted by inflationary models, where quantum fluctuations were stretched to cosmic scales as the universe expanded rapidly in its first moments. However, recent analyses of Planck data suggest that the largest scale temperature variations are weaker than expected. The power at these scales appears slightly lower than predictions, raising the possibility that inflation did not play out exactly as assumed. One particularly interesting anomaly is the lack of temperature variations on the largest scales. The standard model predicts that there should be fluctuations, even at these vast cosmic distances, but observations show that they are weaker than expected. This could suggest that something about the very early universe limited how large these variations could become. Some researchers have speculated that this might be a hint that inflation had a finite duration rather than continuing indefinitely as some models suggest. Others have considered the possibility that this pattern could be a sign that the universe is connected to a larger structure, with physics beyond our observable cosmos influencing its early development. Recent studies have also explored whether new physics might be hiding in the fine details of temperature variations. One area of focus has been the possibility that exotic particles in the early universe influenced how these fluctuations formed. For example, if unknown forms of dark matter or additional neutrino species were present, they could have left subtle imprints in the CMB that would slightly alter the expected distribution of temperature variations. Some models suggest that interactions between dark matter and normal matter in the early universe could have dampened certain fluctuations, leading to a slight deviation from the predictions of the standard model. The level of precision required to detect these tiny anomalies is immense, and scientists must account for a range of possible sources of error. Foreground emissions from our own galaxy, for example, can create patterns in CMB temperature maps that might be mistaken for real cosmic signals. To address this, astronomers use multiple frequency bands to separate true CMB fluctuations from local interference. The challenge is that even after accounting for these effects, some unexplained patterns remain. One ongoing debate is whether certain anomalies in the temperature data are signs of systematic issues in the way measurements are made, or if they genuinely point to new physics. The Planck team has taken great care in refining their data processing techniques, and independent groups have reanalyzed the data to check for biases. So far, the most puzzling trends, such as the low power at large scales and the hemispherical asymmetry, persist, suggesting that they are not simply artifacts of measurement errors. Looking ahead, future missions like the proposed PICO satellite, for example, aim to offer another step forward in resolution and sensitivity. Ground-based observatories, such as the Simons Observatory, will also contribute by targeting specific frequency bands to further refine our understanding of CMB fluctuations. Detecting the undetectable. Techniques for observing primordial gravitational waves. Unlike the gravitational waves detected from black hole mergers, which produce ripples in spacetime that can be observed with current instruments, primordial gravitational waves are far weaker. These waves, if they exist, would have been generated in the first fractions of a second after the Big Bang, stretching and squeezing space itself. Capturing such faint signals requires not just precise instruments, but entirely new ways of observing the cosmos. As these waves traveled through the early universe, they would have left behind a subtle twisting pattern in the polarization of the CMB. This B-mode polarization is one of the primary targets for experiments aiming to detect these ancient ripples in space-time. Unlike temperature fluctuations in the CMB, which have been studied in great detail, B-mode polarization is much harder to measure. It requires instruments with extreme sensitivity, capable of distinguishing these weak signals from other sources of cosmic noise. Ground-based telescopes, such as the South Pole Telescope and the Atacama Cosmology Telescope, are equipped with specialized detectors to scan the sky for signs of B-mode polarization. These observatories are located in remote, high-altitude regions to minimize interference from Earth's atmosphere, which can distort microwave signals. Space-based missions offer another approach to detecting these signals. NASA and the European Space Agency have proposed next-generation satellites, designed specifically for this task with greater accuracy than ever before. Unlike ground-based telescopes, space-based instruments can avoid atmospheric interference entirely, providing a clearer and more precise view of the early universe. Another technique for detecting these waves involves laser interferometry. However, the wavelengths of primordial gravitational waves are vastly longer, requiring interferometers on an unprecedented scale. The proposed LISA, or Laser Interferometer Space Antenna, mission aims to deploy a trio of spacecraft in orbit around the Sun, forming a giant triangle millions of kilometers across. This setup would allow LISA to detect ultra-low frequency gravitational waves that ground-based detectors cannot observe. While LISA's primary mission is to study waves from supermassive black holes, it could also help place new constraints on the strength of primordial gravitational waves. Pulsar timing arrays represent another innovative approach to detecting these ancient signals. Pulsars are rapidly spinning neutron stars that emit beams of radio waves with extraordinary precision. By monitoring the timing of these pulses across a network of pulsars distributed throughout the galaxy, astronomers can look for tiny deviations caused by passing gravitational waves. Although pulsar timing arrays are more suited for detecting waves from merging black holes, they could also reveal hints of primordial gravitational waves if the right conditions are met. Long-term monitoring of pulsars with next-generation radio telescopes, such as the Square Kilometre Array, could improve sensitivity to these faint signals. Different models of cosmic inflation predict different strengths and patterns of gravitational waves, meaning that a successful detection could help determine which inflationary scenario best describes the early universe. Some theories even suggest that the absence of primordial gravitational waves at a certain level could rule out standard inflation entirely, pointing toward alternative explanations for the origin of the universe. Quantum signatures in gravitational waveforms. The gravitational waves detected so far have come from merging black holes or neutron stars, sending signals that match predictions made by Einstein's general relativity. But some scientists believe that these waves might carry even more information, traces of quantum processes from the earliest moments of the universe. One way that quantum effects might appear in gravitational waves is through something called quantum fluctuations. In the early universe, space itself was filled with tiny, random energy fluctuations caused by quantum uncertainty. Normally, these fluctuations remain too small to detect, but during cosmic inflation, these quantum variations were stretched to much larger scales. Some of these fluctuations could have created ripples in spacetime, forming gravitational waves with unique quantum signatures. If such signals exist, they would look different from the gravitational waves produced by merging black holes or neutron stars. Standard gravitational waves have smooth, predictable waveforms that match the equations of general relativity. But quantum signatures could introduce tiny distortions or irregular patterns in these waves, subtle imprints that do not fit into classical physics. Some theories even predict that gravitational waves could carry entanglement, a strange quantum connection where two particles, or even two regions of spacetime, remain linked, no matter how far apart they are. Detecting these quantum effects in gravitational waves would require instruments far more sensitive than those currently in use. Observatories like LIGO and Virgo are already capable of measuring incredibly small changes in spacetime, distortions thousands of times smaller than an atom. But quantum signatures would be even fainter, possibly requiring new detection methods beyond what current laser interferometers can achieve. One possible approach involves studying the statistical properties of gravitational wave signals rather than just individual waveforms. If quantum effects are present, they might cause slight variations in the way waves are distributed over time or across different events. Some researchers have even proposed using quantum experiments on Earth to simulate aspects of gravitational waves. By creating controlled conditions where quantum particles interact with artificial gravitational fields, scientists could test whether certain quantum signatures appear. These experiments would not replace real gravitational wave observations, but they could provide clues about what to look for in space. If quantum signatures in gravitational waves are confirmed, it would suggest that gravity itself has a quantum nature, challenging the long-standing separation between Einstein's theory of relativity and quantum mechanics. This could open the door to entirely new theories of quantum gravity, perhaps bringing us closer to understanding the true nature of space, time, and the universe's origins. Non-standard inflation and its gravitational imprint. The theory of cosmic inflation helps explain why the universe looks so uniform on large scales, why distant regions have similar temperatures, and why space appears nearly flat instead of curved. But what if inflation didn't happen exactly as we think? Well, what if there were variations, non-standard forms of inflation, that left behind subtle but detectable imprints? One alternative is the idea of multi-field inflation. Instead of just one field driving inflation, multiple interacting fields could have shaped the expansion. In this scenario, different fields could have influenced spacetime in different ways, leading to variations in how gravitational waves formed. Some of these waves might have been stronger or weaker than expected, while others could have distinct polarization patterns. Another possibility is intermittent or staggered inflation, where inflation did not happen in one smooth burst, but instead started, stopped, and restarted in a series of phases. This kind of stop-and-go expansion could have created unexpected distortions in gravitational waves, introducing irregularities in their frequency or amplitude. Instead of a single, continuous spectrum of primordial waves, scientists might see gaps, peaks, or other anomalies that don't fit within standard models. Some non-standard models even suggest that inflation might not have been purely an expanding process. In ekpyrotic inflation, inspired by string theory and higher dimensional physics, the universe might have gone through a contracting phase before inflation kicked in. In this scenario, the Big Bang wasn't the true beginning, but rather a transition from a previous state of contraction to a rapid expansion. The idea of warm inflation challenges another fundamental assumption about how inflation worked. In the standard model, inflation occurred in a cold, empty vacuum, with almost no particles present until the expansion slowed down and energy was released. But in warm inflation, the inflaton field continuously interacted with other particles during the expansion. Even if current observations do not yet show clear signs of non-standard inflation, our ability to detect faint signals continues to improve. The possibility that inflation was more complex than we assume remains open, and future observations might reveal the full story of how the universe's first moments shaped everything that followed. Cosmic phase transitions, imprints on gravitational and CMB data. In the earliest moments of the universe, matter and energy existed in an extreme state, vastly different from what we observe today. The universe was hot, dense, and rapidly expanding, undergoing dramatic shifts in its fundamental structure. These shifts, known as cosmic phase transitions, were moments when the nature of particles and forces changed, much like how water turns into ice when the temperature drops. One of the most significant phase transitions is thought to have occurred when the fundamental forces of nature separated. In the first fraction of a second after the Big Bang, all the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. As the universe expanded and cooled, these forces began to split apart. The first such transition would have been the separation of gravity from the other forces, followed by the breaking apart of the strong nuclear force and then the weak and electromagnetic forces. These transitions were not smooth or gradual. They happened in bursts, where the universe's structure changed suddenly. One of the most intriguing phase transitions relates to the Higgs field, which gives particles their mass. In the early universe, the Higgs field likely existed in a different state than it does today. As the universe cooled, the Higgs field underwent a transformation, settling into its current form and allowing particles like electrons and quarks to gain mass. If this transition was abrupt, it could have generated powerful shock waves that disturbed spacetime itself. If the transition was more gradual, it could have left behind remnants, bubbles of different physical states that merged together. These bubbles could have produced gravitational waves as they expanded and collided, potentially leaving an imprint on today's observable universe. Some theories propose that our universe may have started in a higher dimensional state and then transitioned into the four-dimensional space-time we experience. Others suggest that what we perceive as dark energy could be the result of a phase transition that is still unfolding. Next-generation pulsar timing arrays may be able to detect faint signals from the early universe. If successful, these observations could reveal whether the phase transitions happened as expected, or whether something unexpected took place in the early moments of cosmic history. Topological transitions beyond traditional cosmic geometry. Topology describes the way space is connected, its overall structure rather than just the objects within it. It determines whether space extends infinitely in all directions, whether it loops back on itself, or whether there are hidden dimensions beyond what we can see. The question of how the universe's topology evolved during its birth is an area of growing interest. One of the key ideas is that during the early moments after the Big Bang, the universe may have undergone sudden topological transitions, changes not just in what it contained, but in the shape and connectivity of space itself. These changes would be more fundamental than phase transitions. Instead, topological transitions would reshape the very fabric of space. A useful way to think about topology is to compare it to different types of surfaces. A flat, infinite plane and a sphere may look similar in small regions, but they have very different overall structures. A two-dimensional being living on a sphere would eventually return to its starting point if it travelled far enough in one direction. The same could be true for our universe. Space could be wrapped in a way that allows it to be finite, yet without boundaries. If the universe were topologically complex in this way, travelling in a straight line for long enough might eventually bring you back to your starting point. However, if the universe transitioned from one topological state to another early on, it could have permanently altered the way space is shaped on a cosmic scale. One possibility is that the universe once had extra dimensions that later shrank or became hidden. During its earliest moments, some of these dimensions may have curled up or collapsed, leaving only the familiar three dimensions we experience today. If such a transition happened, it could have altered the way matter and energy moved in the early universe. Another intriguing possibility is that the universe began with a more complex shape and later smoothed out into the structure we see today. Instead of expanding from a single point, space could have been highly connected, with multiple paths leading to the same location. If this were true, the large-scale geometry of the universe might not be as simple as it appears. Another approach is to study the large-scale distribution of galaxies. If the universe underwent a topological transition, it might have influenced how galaxies formed, possibly creating unexpected alignments or symmetries in their arrangement. Future galaxy surveys with powerful telescopes could reveal whether these patterns exist. There is also the question of whether topological transitions could still be happening. If the fabric of space can change its connectivity, it raises the possibility that the universe is not in its final state. Some theories suggest that certain regions of space could still be undergoing subtle shifts in their topology, perhaps due to unknown physical processes. These changes might be too small to detect with current technology, but they could have long-term effects on the structure of space-time. Some researchers have proposed that dark energy could be a sign that space is still shifting in its fundamental shape. If true, this would mean that the nature of the universe is still evolving. The study of cosmic topology is still in its early stages, but as observational techniques improve, scientists may be able to uncover the hidden geometry of the cosmos, revealing secrets about its earliest moments. Quantum entanglement on a cosmic scale. When two particles become entangled, they remain connected in such a way that measuring one instantly affects the other, no matter how far apart they are. This effect has been repeatedly confirmed in laboratories on Earth, where entangled particles seem to share information faster than light should allow. While entanglement is usually associated with subatomic particles, some physicists have begun to wonder if this strange connection could extend beyond the microscopic world, perhaps influencing the structure of the universe. The idea suggests that galaxies, clusters, and even entire cosmic filaments may be connected in ways that standard physics does not yet fully describe. Instead of being shaped only by gravity and dark matter, the arrangement of the universe's larger structures might also be influenced by entanglement, an invisible web of connections spanning vast distances. Just after the Big Bang, everything in the cosmos was packed into an incredibly small space. Quantum effects, which normally dominate the behavior of tiny particles, would have played a crucial role in shaping the universe's initial conditions. As the universe expanded, quantum fluctuations would have stretched across vast regions of space. According to some theories, these fluctuations could have carried entanglement with them, linking distant parts of the universe in ways that are difficult to detect today. The CMB is nearly the same temperature in all directions, which is puzzling because light would not have had time to travel across the entire universe and even out the differences. The standard explanation for this is cosmic inflation. But if quantum entanglement connected different regions of the universe from the very beginning, it could provide an alternative explanation for why the CMB is so uniform. Distant areas might have been linked even before light had a chance to travel between them. Some physicists have proposed that dark energy could be related to quantum entanglement on a massive scale. If distant galaxies or even entire cosmic structures are entangled, this connection might influence how space expands over time. Similarly, dark matter, which interacts with gravity but not with light, might be explained if some unseen form of entanglement is affecting how ordinary matter behaves on cosmic scales. Testing these ideas is challenging, but some experiments and observations might provide clues. One possible approach is to look for patterns in the large-scale structure of the universe that cannot be explained by gravity alone. If entanglement is playing a role, it could create subtle correlations between galaxies and clusters that do not fit with standard models. There is also growing interest in whether black holes might be key players in cosmic entanglement. The holographic principle suggests that information about everything inside a black hole might be encoded on its outer surface, similar to how a hologram stores three-dimensional information on a two-dimensional surface. Some researchers believe this idea could extend to the entire universe, meaning that everything we experience might be connected through an underlying entangled framework. If true, black holes could serve as natural laboratories for studying entanglement on scales far beyond the quantum realm. While the idea of cosmic scale entanglement is still speculative, it offers a fresh way of thinking about the deep connections within the universe. It raises questions about whether space itself is an emergent property of entangled information, rather than something that simply exists on its own. Information theory meets cosmology, the fabric of reality. Information theory, originally developed to study communication systems, has found surprising applications in cosmology, raising the possibility that the fabric of the universe is woven from information in the same way a computer processes data. One of the key ideas in this approach is that everything in the universe, from atoms to galaxies, can be described in terms of bits of information. A bit is the smallest unit of information, representing a choice between two possibilities, like a coin flip landing on heads or tails. Some physicists have suggested that space, time, and even matter itself might emerge from the way these fundamental bits of information are arranged and processed. If true, this would mean that the universe behaves less like a collection of physical objects and more like a vast computational system. The standard view is that the universe began with the Big Bang. However, if information is at the core of reality, then the Big Bang might not have been a purely physical explosion, but rather a transformation in the way information was structured. Some researchers have proposed that before the Big Bang, information existed in a different form, perhaps as a kind of quantum code that later gave rise to the universe as we observe it today. A long-standing puzzle in physics is what happens to the information contained in objects that fall into a black hole. According to classical physics, this information should be lost forever, but quantum mechanics suggests that information can never truly be destroyed. This paradox has led to the idea that black holes may store information on their surface, a concept called the holographic principle. Some physicists have taken this idea even further, proposing that the entire universe might work the same way. If this is true, then the universe itself might function like a massive quantum computer, with the laws of physics acting as the rules that process information. If the universe is fundamentally based on information, then time might not be a smooth, continuous thing at all. Instead, it could be more like a sequence of discrete steps, similar to how a computer processes data one operation at a time. This idea could help explain some of the mysteries of quantum mechanics, where particles can exist in multiple states at once and seem to jump from one place to another without passing through the space in between. Some researchers have suggested that the structure of space itself might be a vast entanglement network. If true, then experiments designed to study entanglement on large scales, such as those involving high-energy cosmic rays, might uncover evidence that the universe is indeed a vast web of information. If the universe operates like a computer, then what runs this cosmic computation? Is there a deeper layer of reality beyond the informational framework we observe? Some scientists have speculated that if the universe is fundamentally computational, it might be possible to create artificial universes through simulations, meaning that our own cosmos could be part of an even larger structure. Despite the speculative nature of these ideas, the intersection of information theory and cosmology is becoming an increasingly active area of research. The growing field of quantum gravity often relies on information-based principles to bridge the gap between the two. The idea that spacetime itself emerges from entanglement, for example, is being explored as a way to explain how gravity works at a microscopic level. Holographic principles, a new look at cosmic origins. The term holographic comes from the idea of a hologram, a three-dimensional image that is encoded on a two-dimensional surface. When light shines on the surface, it creates the illusion of a three-dimensional object. The holographic principle extends this idea to the cosmos. In the 1970s, physicist Stephen Hawking discovered that black holes emit radiation, which led to the famous information paradox. According to classical physics, anything that falls into a black hole is lost to the universe, including any information about it. However, this directly contradicts the principles of quantum mechanics, which state that information cannot be destroyed. The question became, if black holes can't destroy information, where does it go? The holographic principle was proposed in part as a solution to this paradox. In the 1990s, physicists such as Gerard T. Hooft and Leonard Susskind developed the idea that the information contained within a black hole could be stored on its event horizon. Instead of being the basic stage on which everything happens, space and time might emerge from a deeper, more fundamental level of reality. How could something as fundamental as the universe be created from information? What does it mean for our experience of space and time if they are just a projection? The holographic principle offers a new perspective on the Big Bang. Instead of being a singular, chaotic explosion from which space and time sprang into existence, the Big Bang might have been a phase transition. Our universe's origin wasn't the creation of space and time from nothing but a shift in the way information was processed, allowing the three-dimensional reality we observe to emerge from a two-dimensional information field. If the universe is a hologram, it suggests that everything we experience, from the stars in the sky to the galaxies that fill the cosmos, is encoded on a distant surface. Every event in the universe, from the formation of stars to the motion of galaxies, could be understood as a kind of projection from this boundary. This suggests that the true reality might lie beyond the familiar space and time we experience. The holographic principle could provide a way to reconcile general relativity and quantum mechanics by suggesting that gravity, like everything else in the universe, is an emergent property of a deeper, information-based structure. In this view, gravity would not be a fundamental force, but rather a consequence of the way information is encoded on the boundary of the universe. Since the information that defines the universe is supposedly encoded on a distant surface, it's not immediately clear how we can observe or interact with that surface. However, recent advances in theoretical physics and cosmology have begun to suggest possible ways to look for signs of the holographic principle in the cosmos. The study of Hawking radiation and the behavior of black holes at the quantum level may offer important insights into whether the holographic principle holds true. In particular, the study of quantum entanglement could offer further evidence that the universe is deeply connected in ways that go beyond our conventional understanding of space and time. Emergent gravity, rethinking the gravitational constant's origin. Why is the gravitational constant, this mysterious value that governs the force of gravity, set at the specific number that it is? Why does it act so differently from the other forces of nature, like electromagnetism or the strong nuclear force? These questions have led some physicists to propose that gravity might not be a fundamental force at all. Rather than assuming gravity as a force that has always been present, independent of the fabric of the universe, emergent gravity theories propose that it could be a byproduct of other, more fundamental phenomena. These phenomena might arise from the behavior of quantum fields, the distribution of matter, or even the dynamics of space-time itself. One of the first serious proposals for emergent gravity came from the physicist Erik Verlinde. Verlinde's work centered on the idea that gravity isn't a fundamental force, but rather a result of the way information is encoded in the structure of space-time itself. According to Verlinde, gravity could be thought of as a kind of entropic force. This means that gravity emerges because of the way entropy behaves in the universe. In this view, gravity is an effect of the statistical behavior of microscopic particles in a system. When matter interacts, it creates a kind of information structure that leads to the emergence of gravitational effects. Verlinde's approach hinges on the idea that the geometry of space-time isn't fundamental, but rather a macroscopic description of deeper quantum processes. He draws parallels to thermodynamics, where temperature and pressure are emergent properties of the microscopic interactions between atoms and molecules. In this analogy, gravity is similar to temperature. It's a large-scale effect that emerges from the underlying microscopic behavior of particles. In emergent gravity models, the gravitational constant, a key value in general relativity, might not be constant at all. Instead, it could be a dynamic quantity that changes depending on the underlying quantum state of the universe. One of the most compelling pieces of evidence in favor of emergent gravity theories comes from the behavior of galaxies. Observations have shown that galaxies seem to rotate in a way that defies the predictions of Newtonian gravity. According to the standard laws of physics, the outer regions of galaxies should be spinning slower than the inner regions because there isn't enough visible matter to generate the required gravitational pull. However, galaxies do not behave this way. Their outer regions rotate at the same speed as the inner parts. One explanation for the discrepancy in galaxy rotation is that dark matter exists in a halo around galaxies, providing the extra gravitational pull needed to explain the observed rotation rates. However, emergent gravity theories offer a different perspective. Verlinde, for instance, suggests that the missing mass in galaxies might not be dark matter at all. Instead, the behavior of the galaxy's outer regions could be a result of the emergent nature of gravity itself, rather than the presence of unseen dark matter. If the gravitational force itself is not a fundamental interaction, then the need for dark matter might not be necessary to explain the observed phenomena. Instead, the behavior of galaxies could be a result of gravity acting in an unexpected way due to the underlying quantum structure of space-time. This perspective does not rule out the existence of dark matter, but it does offer a new approach to understanding how galaxies behave and how the universe's fundamental forces operate. In the standard model of physics, the gravitational constant, denoted as g, is a fixed number that governs the strength of gravity. But in emergent gravity theories, g could vary depending on the conditions in the universe. This variability could explain certain cosmological puzzles, such as the observed accelerated expansion of the universe. In some emergent gravity models, what we perceive as dark energy could also be an effect of gravity acting in a way that is not fully understood. This theory offers a fresh perspective on the evolution of the cosmos, especially in the early universe. In the moments immediately following the Big Bang, the laws of physics were likely very different from the ones we observe today. In an emergent gravity framework, the early universe's gravitational behavior could have emerged gradually as the quantum fields that governed the universe interacted and evolved. The forces of nature that we now take for granted, gravity included, might have emerged from quantum fluctuations and interactions that occurred in the primordial soup of the early universe. If spacetime is not fundamental but emerges from underlying quantum processes, this could explain phenomena like the formation of large-scale structures in the universe, the CMB, and even the behavior of black holes. Instead of being a static backdrop for events in the cosmos, spacetime could be a dynamic, evolving entity shaped by quantum forces. The idea of emergent gravity is still in its early stages. Theoretical physicists continue to explore the mathematical implications of these ideas, while observational cosmologists are searching for clues that might support or challenge these theories. Might the distribution of galaxies and the structure of the cosmic web offer hints about the nature of gravity? These are questions that could one day be answered as we push the boundaries of our understanding. Non-equilibrium dynamics in the early universe. The concept of equilibrium is something we encounter often in our everyday lives. It's the state where everything has reached a balance, and no significant changes occur unless something disturbs that balance. For example, when you place ice cubes into a warm drink, the ice melts until the temperature of the drink and the ice cubes equalizes. This is an example of equilibrium. In the cosmos, equilibrium implies a stable, unchanging condition. But in the early universe, the conditions were far from that. Instead, the universe was in a non-equilibrium state, where things were rapidly evolving and physical processes were happening at breakneck speeds. This extreme state of change is what many scientists believe was key to the formation of the universe as we know it today. Theories in cosmology that deal with non-equilibrium dynamics are not just about the moments after the Big Bang, but also touch on how the universe continued to evolve in the first few moments of its existence, shaping everything from the formation of the first particles to the birth of galaxies. Right after the Big Bang, there wasn't enough time or space for particles to reach a stable equilibrium, and as a result, they were constantly interacting, colliding, and undergoing transformations. The universe was in a constant state of flux, and this flux played a crucial role in shaping the path the universe would take. Even after the period of inflation, the universe remained far from equilibrium. For instance, shortly after inflation, the universe cooled enough for particles like quarks, gluons, and electrons to form. These particles weren't in a calm, orderly state. They were still undergoing rapid interactions, decays, and collisions. As the universe continued to expand and cool, different phases of matter emerged, each with their own non-equilibrium dynamics. In particular, the process of baryogenesis, which is thought to have occurred during the early universe, was driven by non-equilibrium conditions. This process led to an asymmetry between matter and antimatter. In theory, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving only radiation behind. However, observations show that we live in a universe that is made almost entirely of matter, with very little antimatter to be found. This imbalance could only have occurred under highly dynamic, out-of-equilibrium conditions. The mechanisms behind this matter-antimatter asymmetry remain one of the key open questions in cosmology. Furthermore, the early universe went through different phases of matter as it cooled, from a quark-gluon plasma to the formation of atoms. Each phase transition was not a smooth, gradual process. Instead, they were sudden, abrupt events, much like water freezing into ice. These transitions happened because of the changing conditions, temperature, density, and the energy levels in the universe, each one of which played a critical role in determining how the universe evolved. For example, during the period of nuclear synthesis, roughly 3 minutes after the Big Bang, protons and neutrons combined to form the first light elements like hydrogen, helium, and lithium. This phase transition was another moment where non-equilibrium dynamics shaped the future of the universe. The rapid cooling during this time, along with changes in the forces and interactions between particles, made it possible for these elements to form, setting the stage for the later formation of stars and galaxies. The universe also went through a phase transition when atoms began to form roughly 380,000 years after the Big Bang. Before this time, the universe was a hot, dense plasma of free electrons, protons, and photons, with no neutral atoms to speak of. As the universe expanded and cooled, electrons and protons combined to form hydrogen atoms in a process called recombination. This phase transition marked the moment when the universe became transparent to light, allowing photons to travel freely through space, thus forming the CMB. The universe has continued to be out of equilibrium as it has evolved. Stars live and die, galaxies collide, and new structures form, all while the universe continues to expand. What's fascinating is that, in some ways, the universe may never have reached a state of complete equilibrium. As we look to the future, we can only speculate on how the universe's expansion and the behavior of dark energy might continue to drive a never-ending series of non-equilibrium processes. In fact, the universe may be in a perpetual state of change, constantly evolving, expanding, and rearranging itself. Novel computational models simulating the birth of the cosmos. At its core, a computer simulation of the universe's birth attempts to model the interactions between all the forces and particles that were present during the first moments of creation. It simulates how space expanded, how matter and energy behaved, and how the earliest structures formed. The beauty of computational physics lies in its ability to take abstract equations and turn them into vivid visualizations, making the invisible processes of the universe's birth more tangible. For decades, physicists have built upon the foundational equations of general relativity, quantum mechanics, and thermodynamics to understand how the universe began. But these theories, while powerful, were never designed to handle the extreme conditions present at the very beginning of the universe. To fill the gap, computational models offer a bridge, using advanced algorithms and the power of modern computing to simulate scenarios that could not be replicated in a laboratory. These simulations are a way to test hypotheses, visualize the evolution of the cosmos, and explore the boundaries of current scientific understanding. One key area where computational models shine is in the simulation of inflation. However, recreating this scenario is not a simple task. The mathematics involved is incredibly complex, and the conditions of the early universe were so extreme that even our best theories struggle to fully explain them. This is where simulations become indispensable. By tweaking the parameters and testing various assumptions, scientists can explore different inflationary models, check how they fit with the data we observe today, and potentially uncover new ways the universe could have evolved. By incorporating quantum mechanics into these computer models, scientists can simulate how the early universe's energy density fluctuated, how matter interacted, and how the first structures began to form. This gives us a glimpse into how the universe, despite being mostly uniform at large scales, contains pockets of irregularity and complexity, such as the clumping of matter that eventually formed galaxies. The development of these simulations also requires the integration of multiple disciplines. Not only do they require a deep understanding of physics, but also advanced knowledge in computer science and mathematics. To model such a complex and multifaceted system, physicists often rely on sophisticated algorithms that can handle vast amounts of data. For example, one of the most common methods is called n-body simulations, which track the movement of large numbers of particles under the influence of gravity. These simulations can model the behavior of galaxies, clusters of galaxies, and even larger structures like the cosmic web. While these simulations are often used for studying later stages in the universe's evolution, their principles can be applied to the early universe as well. In combination with simulations of cosmic inflation and quantum fluctuations, they provide a comprehensive picture of how matter and energy interacted in the early universe. As powerful as these computational tools are, they still face significant challenges. One of the major obstacles is the sheer scale of the problem. The universe is unimaginably vast, and simulating its birth involves tracking every interaction of particles, fields, and energy densities across enormous volumes of space and time. Simulations today can model the evolution of small portions of the universe, or they can look at large-scale cosmic features like the growth of galaxies or the behavior of dark matter. However, simulating the universe in its entirety at the level of individual particles would require an immense amount of computational power, well beyond what we can currently achieve. For this reason, scientists often simplify their models by focusing on specific aspects of the universe's formation, allowing them to gather insights without overwhelming the limitations of current technology. Despite these limitations, computational models have already provided remarkable insights into the nature of cosmic birth. They've helped clarify how structures like galaxies and stars form from the gravitational collapse of matter. Through simulations, we've also gained new perspectives on phenomena like cosmic inflation, dark matter, and dark energy, offering potential explanations that go beyond conventional wisdom. By training AI systems to identify patterns in massive datasets or to predict outcomes in complex models, scientists could speed up the process of simulation and gain new insights that might have been difficult to uncover using traditional methods. Machine learning algorithms could be trained to recognize subtle features in simulations that correlate with real-world observations, allowing scientists to focus on the most promising theories: the role of exotic matter in cosmic genesis. In recent years, some theories have started to explore the role of exotic forms of matter that go beyond the standard model of particle physics, suggesting that these unusual substances could have played a key role in shaping the universe as we know it. In the world around us, matter is composed of atoms, which in turn are made up of protons, neutrons, and electrons. These particles interact according to the known rules of the Standard Model, which has served as the backbone of particle physics for much of the last century. But this model, despite its successes, has its limits. There are many aspects of the universe that it cannot explain. To account for this, some have turned their attention to more exotic forms of matter. Some of the most promising candidates for dark matter are exotic particles. These hypothetical particles, such as WIMPs or axions, are predicted to be far more abundant in the early universe than they are now, suggesting that they may have been essential in shaping the formation of structures like galaxies and clusters. Some theories suggest that dark matter particles might have been produced during the first few moments of the Big Bang, perhaps during a process known as reheating. As the universe cooled, these particles could have settled into gravitational wells, clustering together to form the scaffolding for galaxy formation. If these particles were indeed abundant during the early universe, they might have acted as a kind of cosmic glue, drawing ordinary matter together and helping to form the large-scale structures we see today. Another area of speculation concerns the potential role of exotic phases of matter that could have existed during the universe's early moments. In high-energy environments, matter behaves differently than we experience in everyday life. The high temperatures and densities that existed just after the Big Bang could have produced exotic phases of matter, substances that we do not observe under normal conditions. For example, quark-gluon plasma is a state of matter in which quarks and gluons, the fundamental building blocks of protons and neutrons, are no longer confined within particles. Instead, they form a hot, dense soup that could have dominated the universe during the first few microseconds after the Big Bang. As the quark-gluon plasma cooled, it eventually transitioned into the familiar protons, neutrons, and electrons that made up atoms. But if this transition occurred differently than we expect, it could have altered the fundamental properties of the universe, perhaps affecting the formation of the first atoms or even the cosmic inflationary period. Researchers are still investigating how these early phases of matter might have shaped the universe's history and what role they may have played in creating the universe's complex structure. Some theories propose the existence of exotic particles that could have existed during the universe's birth, such as prions, which are thought to be the building blocks of quarks and leptons. In some models, prions could have been the fundamental particles of the universe in its earliest moments. They might have given rise to the very forces and particles we observe today. Moreover, some theories speculate about the existence of new forces of nature that could have governed the universe's early evolution. These forces might have acted alongside gravity, electromagnetism, the weak force, and the strong force. Theoretical models of extra-dimensional spacetime suggest that such forces might have had profound effects on the way matter behaved and interacted in the universe's infancy. One intriguing idea is that the universe could have gone through a pre-Big Bang phase, in which exotic forms of matter existed before the traditional Big Bang event. During this pre-Big Bang era, exotic matter, potentially involving new forms of particles or interactions, could have played a role in laying the groundwork for the universe that followed. It has been proposed that exotic particles, such as those from a higher dimensional or quantum mechanical origin, could have been responsible for driving inflation itself. These particles could have interacted with spacetime to produce the rapid expansion, laying the foundation for the universe's structure. In the realms of quantum mechanics and general relativity, matter and energy are intimately connected through equations like Einstein's famous E equals mc squared. Yet these equations are based on our understanding of matter as we experience it on a daily basis. And they may not be sufficient to describe the universe's earliest moments, when conditions were far outside the realms of our current knowledge. If exotic forms of matter were involved, we may need new frameworks or theories to describe how these substances behaved, interacted, and influenced the universe's evolution. Causality and time's arrow, rethinking the first moments. We have clocks, calendars, and the ticking of seconds to measure the passage of time. But before the universe began, or during the first few moments of the Big Bang, was time itself even a meaningful concept? The classic view, stemming from general relativity, suggests that time began with the Big Bang, that the universe and time itself were birthed in that moment. Yet as we peer deeper into the mysteries of cosmology and quantum mechanics, we begin to question whether time was indeed a straightforward progression from the moment of creation. Causality, too, plays a central role in our understanding of the universe. The principle of causality states that every effect has a cause. In the normal flow of events, we can trace a chain of cause and effect from one moment to the next. However, when looking at the universe's origins, some theorists suggest that our traditional understanding of cause and effect might break down. The concept of causality is intricately tied to the arrow of time, the idea that time moves in one direction, from the past, through the present, and into the future. The arrow of time is a fundamental feature of how we experience the world, but it is also a topic of great debate in modern physics. For centuries, we've believed that the universe began in a singular event, the Big Bang, and that this event marked the beginning of both time and causality. But as cosmologists delve deeper into the mysteries of the cosmos, they're beginning to wonder if the arrow of time we experience, with its familiar direction from past to future, is a feature of the universe's large-scale evolution, rather than a basic feature of reality itself. At the quantum level, things behave in ways that are radically different from what we experience in the macroscopic world. Particles can exist in multiple states at once. They can be entangled across vast distances, and they can even seem to break the rules of causality altogether. If quantum mechanics was responsible for the creation of the universe, Could time and causality have operated in a fundamentally different way in the very beginning? Could events unfold in a manner where cause and effect were not clearly linked, or even where time as we understand it did not apply? One theory, known as the block universe model, proposes that time is an illusion and that all events, past, present, and future, exist simultaneously in a kind of cosmic block where every moment is already set. Instead of a clear chain of causes and effects, the entire timeline of the universe could already be laid out, with every event predetermined. This would imply that the universe and all its events were baked in from the very beginning, and that our perception of time as flowing from one moment to the next is simply an illusion. Inside this event horizon of a black hole, the normal flow of time and space is thought to distort and warp beyond recognition. If time can behave so strangely at the event horizon of a black hole, could it have behaved similarly in the early universe during the first moments after the Big Bang? Could the birth of the universe have involved a breakdown of the usual causal relationships, where time itself was not a simple, linear progression? Some theories of quantum gravity propose that the quantum fluctuations of spacetime could have caused tiny, unpredictable bounces or jumps in the structure of the universe. Instead of the smooth, continuous unfolding of time that we experience today, the early universe could have been marked by chaotic, nonlinear transitions that defy our current understanding of cause and effect. Some of the patterns observed in the CMB, such as temperature fluctuations and polarization patterns, could be signs of quantum mechanical processes at work during the universe's infancy. If these fluctuations were caused by quantum processes, they might have been influenced by events that defy our classical understanding of causality. For example, if quantum entanglement or other non-local effects were at play, they could have influenced the evolution of the universe in ways that challenge cause and effect. Cosmological observatories of the future, pushing the detection frontier. As we strive to unravel the mysteries of the universe's birth, the next generation of cosmological observatories promises to take us closer than ever before to the edge of understanding. These instruments, some of which are already in development and others that are still years or even decades away, will provide new and exciting ways to observe the cosmos in unprecedented detail. From detecting the faintest gravitational waves to capturing the first moments of the universe's formation, these missions will push the boundaries of what we know about the cosmos, allowing us to look deeper into the past than ever before. While the JWST primarily focuses on observing distant galaxies and stars, its infrared capabilities have already, and will continue to, provide us with a wealth of information about the early universe. The telescope's infrared sensitivity allows it to peer through cosmic dust and see objects that are far too faint or distant for current telescopes to observe. This includes the potential to detect the first galaxies that formed after the Big Bang, and even witness the formation of stars and planetary systems in the distant past. The JWST is designed to study the universe's earliest epochs, including the cosmic dawn, when the first light from stars began to shine. It will help us understand the processes that shaped the early universe, shedding light on how galaxies and other cosmic structures began to take shape. But its capabilities don't stop there. Beyond the JWST, several other missions are currently in the planning stages, each with the potential to reveal new layers of the universe's history. LISA, which is set to launch in the 2030s, will consist of a constellation of 3 spacecraft arranged in a triangular formation, each equipped with lasers that can detect even the faintest ripples in space-time. The spacecraft will be positioned millions of kilometers apart, and the tiny changes in the distance between them caused by passing gravitational waves will be measured with remarkable precision. This method will allow LISA to detect waves with wavelengths much longer than those detectable by ground-based observatories, opening up a new era of gravitational wave astronomy. Another exciting project in the pipeline is the Square Kilometre Array, or SKA, a massive radio telescope that will be built across 2 continents in South Africa and Australia. The SKA will be the largest and most powerful radio telescope ever built, with the potential to provide a new level of detail in our understanding of the universe. One of the SKA's most ambitious goals is to map the large-scale structure of the universe in unprecedented detail, helping us trace the evolution of galaxies and clusters over cosmic time. By studying the distribution of galaxies and the cosmic web they form, we will be able to learn more about the forces that shape the universe's growth and expansion. By measuring the distances between galaxies with extraordinary precision, the SKA will provide valuable insights into the effects of dark energy on cosmic expansion. The SKA's radio capabilities will provide us with a new way to probe the universe's infancy and the forces that shaped its evolution. While these observatories will provide a wealth of information about the early universe, they will also be complemented by other groundbreaking missions focused on exploring the cosmos in new ways. For instance, the upcoming Euclid mission by the European Space Agency is designed to investigate the nature of dark energy and dark matter by creating detailed 3D maps of the universe. By studying the way light from distant galaxies is bent and distorted by dark matter, Euclid will help scientists uncover the properties of these mysterious substances and their role in the universe's expansion. To detect primordial gravitational waves, scientists are developing specialized instruments and observational strategies. One such effort is the proposed Cosmic Explorer, a ground-based observatory that would be dedicated to detecting low-frequency gravitational waves, particularly those that originated during the earliest moments of the universe. With its sensitivity and advanced detection methods, the Cosmic Explorer could provide groundbreaking data that helps unlock the mysteries of the universe's formation. Another innovative project is the Event Horizon Telescope Array, a global network of radio telescopes that aim to capture images of black holes. While the EHT has already made history by producing the first image of a black hole in 2019, its future iterations may provide even more detailed observations of supermassive black holes, particularly those at the centers of distant galaxies. These observations could reveal new insights into the nature of gravity, spacetime, and the physics of extreme environments. Cosmic simulations. Are we living in a universe-scale experiment? As our understanding of the universe deepens, one provocative idea has emerged that blurs the lines between science and philosophy. The possibility that our entire universe could be a simulation. This concept, popularized by the philosopher Nick Bostrom in 2003 through his simulation hypothesis, suggests that advanced civilizations might possess the technological capability to simulate entire universes, complete with their own physical laws, history, and even sentient beings. In this view, what we experience as reality could be nothing more than a vast, complex simulation, perhaps indistinguishable from the real world in every way. The idea of a simulated universe challenges fundamental assumptions about existence, reality, and our place in the cosmos. But while it may sound like science fiction, the notion has been taken seriously by a number of prominent scientists and philosophers. In fact, some physicists argue that there may be detectable signs or evidence that could support this hypothesis. At the core of the simulation hypothesis lies a question that seems simple at first glance. How do we know that the universe we observe is the real one? After all, our experience of reality is shaped by our senses, which can be deceived, and by the information we receive from external sources, such as instruments and telescopes. If advanced civilizations could create incredibly sophisticated simulations, could we ever be certain that we aren't living in one? This question raises interesting challenges for scientists who are investigating the very nature of reality itself. One avenue of research that has gained traction is the search for inconsistencies or glitches in the fabric of the universe. If our universe is a simulation, there might be some kind of imperfection, a sign that it is not truly real. This idea is similar to the way we detect errors or inconsistencies in computer simulations, such as those used in climate models or video games. If our universe operates like a simulation, there might be subtle, detectable patterns or irregularities, such as pixel-like structures or limits to physical laws, that suggest our reality is artificially constructed. Some scientists point to the concept of quantum discreteness as a potential clue. In quantum mechanics, space and time appear to be fundamentally granular rather than continuous. This means that at the smallest scales, the universe might not be smooth and unbroken, but instead consists of tiny, indivisible units, much like pixels in a digital image. If this discreteness is real, it could be evidence of a simulated universe, where the laws of physics are programmed in such a way that the universe operates on discrete chunks of information. Researchers have speculated that one day we might be able to measure the graininess of spacetime, potentially revealing the simulation's underlying structure. Another potential clue is the nature of the cosmic constants, the numbers that govern the fundamental forces of nature, such as the strength of gravity or the speed of light. These constants appear to be finely tuned in a way that allows life, as we know it, to exist. Some have wondered if this fine-tuning could be a sign of a simulation that was deliberately designed with specific parameters. The idea is that if we live in a simulation, the creators of that simulation would have set these constants to ensure the universe functions in a stable and predictable way. Just as an engineer might design a virtual world where the rules are fixed, the constants we observe could be part of a grand design. While these speculations may sound intriguing, it's important to note that there is no direct evidence supporting the simulation hypothesis, and many scientists are skeptical of it. The very idea of a simulation raises questions about what constitutes reality, and whether the question of whether the universe is real is even meaningful. Some philosophers argue that even if our universe were a simulation, it would still be real in the sense that it is real to us. Our experiences, our perceptions, and our lives are real, even if they are generated by a computer program. In this sense, the simulation hypothesis becomes less about proving or disproving the nature of reality, and more about rethinking our understanding of existence itself. If our universe is a simulation, it suggests that there might be higher intelligences that created and control it. These beings could possess technology far beyond our current understanding, and perhaps even have the ability to manipulate the fundamental laws of physics in ways that we can't even begin to imagine. If we are living in a simulation, could these intelligences be aware of us? Could they observe our actions, study our behavior, and even interact with us in ways that are beyond our comprehension? If an advanced civilization could create a simulated universe, what does that say about the origins of our own universe? Could the Big Bang have been the beginning of a simulated reality, created by some higher intelligence for purposes we may never fully understand? This idea could help explain some of the mysteries of cosmology, such as the fine-tuning of the universe and the apparent randomness of quantum events. It also raises important questions about the relationship between physical reality and digital or virtual realms, questions that are not only central to our understanding of the cosmos, but to the future of technology and artificial intelligence. A number of experiments have been proposed to look for signature errors in the CMB. If the universe were a simulation, certain patterns or anomalies might appear in the CMB, like the glitches in a computer game or the artifacts left behind by a digital rendering process. While these experiments are still in the early stages, they represent a novel way of thinking about the fundamental nature of reality. As technology continues to advance and our ability to simulate complex systems improves, it's possible that we may one day be able to answer this question, at least in part. Until then, the possibility that our universe is a grand cosmic experiment run by an advanced intelligence will remain one of the most fascinating and mysterious ideas in the study of the cosmos. Entropy in reverse, the possibility of a universe that rewinds its history. The second law of thermodynamics, one of the cornerstones of modern physics, states that in a closed system, entropy, essentially a measure of disorder, must always increase over time. This means that the universe, from the moment of the Big Bang, has been moving in a specific direction, toward greater disorder, randomness, and decay. The stars burn out, energy dissipates, and systems become less organized as time progresses. Yet, in the world of theoretical physics, there are some intriguing ideas that challenge this seemingly immutable law, suggesting the possibility of a universe that might sometimes rewind itself, effectively decreasing in entropy and reversing its history. This idea seems almost counterintuitive because it defies the fundamental understanding of time. In everyday life, we experience time as a constant forward motion. Our lives unfold in one direction. We age, the sun rises and sets, and events happen only once. But what if there were a way, at least theoretically, for the universe to move backward in time, decreasing in entropy as it does so? This question takes us into some of the more speculative and mind-bending territories of modern physics, where concepts like time reversal, closed time-like curves, and even the nature of causality come into play. One potential way the universe could reverse its entropy involves the nature of time itself. Time, as we perceive it, is intricately linked to the progression of events. Some theories propose that at very small scales, such as the realm of quantum particles, the flow of time could be reversible. If this were true, then it might suggest that under certain conditions, the larger structure of the universe could, at least for brief moments, rewind itself, reversing the increase in entropy. The concept of entropy itself, in a more detailed sense, can be thought of as the spread of energy within a system. When energy becomes more evenly distributed, entropy increases. In a highly ordered system, entropy is low. The progression toward higher entropy reflects the universe's natural tendency to move toward equilibrium, where all things are spread out as evenly as possible. However, if the universe was somehow to experience a reverse process, the energy distribution could become more concentrated again, potentially leading to a lower entropy state. One speculative model that explores this possibility is known as a Boltzmann brane scenario. This hypothesis posits that in the far future, as the universe continues to expand and entropy increases, there could be fluctuations in the quantum field that temporarily lower entropy in small regions of space. These fluctuations could, in theory, form isolated pockets of order, such as a functioning brain with memories of its past, though not necessarily connected to any larger system. The idea behind this thought experiment is that if these fluctuations can occur in small regions, there could be a rewinding of entropy within those regions, however fleetingly. While this idea is largely theoretical, it suggests that entropy may not always follow a perfectly predictable path, and in some cases, it could briefly decrease. Beyond these isolated pockets, another way to consider the reversal of entropy might lie in the concept of the Big Crunch. The Big Crunch is a potential end scenario for the universe, where the expansion of the cosmos, which has been ongoing since the Big Bang, eventually reverses itself, and gravity causes everything to collapse inward. In this scenario, the universe would contract back to a singularity, much like the state it was in before the Big Bang. As the universe contracts, entropy could be reversed, with matter and energy becoming more tightly concentrated again. While current observations suggest the universe is expanding at an accelerating rate, driven by dark energy, the idea of the Big Crunch still serves as a theoretical model in which the universe might rewind its history in a dramatic, large-scale way. If the universe were to collapse in this manner, it might imply that the increase of entropy is not necessarily a one-way process, and that a reversal is at least mathematically possible. Another intriguing aspect of this discussion centers on closed time-like curves, which are solutions to Einstein's equations of general relativity that allow for the possibility of time loops. In simple terms, a closed time-like curve is a path through spacetime that loops back on itself, creating a closed loop in time. These loops would allow for an event to occur, and then, because of the nature of the curve, occur again, potentially leading to a reversal of entropy within that localized region. In theory, if a region of space-time were to form such a curve, the flow of time could, in some sense, be reversed. However, this leads to all sorts of paradoxes, such as the famous grandfather paradox, where a person traveling back in time could potentially alter events in such a way as to prevent their own existence. These paradoxes highlight the challenges of reconciling time travel and time reversal with the laws of physics, especially when it comes to causality, the idea that cause precedes effect. Yet, despite the theoretical challenges, the concept of closed time-like curves is taken seriously by some physicists. Certain solutions to general relativity's equations, such as the rotating black hole known as a Kerr black hole, predict the existence of such curves. These solutions suggest that time travel, or the reversal of time's arrow, might be possible in extremely specific conditions that are far beyond our current technological capabilities, but still mathematically plausible. If time itself can bend and twist in such ways, the reversal of entropy could follow suit, as energy and matter might find themselves in states of lower disorder, at least temporarily. In quantum mechanics, particles are governed by probabilities rather than deterministic laws. This opens up the possibility that at a very small scale, the rules of entropy might behave differently, allowing for localized decreases in disorder. Quantum entanglement suggests that information can be transferred in ways that might allow for non-local reductions in entropy. While entanglement does not imply time reversal directly, it challenges our conventional understanding of information flow and could hint at the possibility of processes that are not constrained by the typical arrow of time. Could the Big Bang itself have been a low entropy state that emerged from a previous phase of higher disorder, perhaps in a cyclical pattern? Might the universe someday rewind itself as part of a cosmic cycle, with entropy decreasing before a new expansion takes place? Could the fluctuations in quantum fields and black hole dynamics allow for localized rewinds of time? These questions remain firmly within the realm of speculation, but by investigating the possibility that entropy might, under certain conditions, reverse itself, we are not just challenging conventional physics. We are rethinking the very nature of time, causality, and the evolution of the universe itself. As science continues to explore these ideas, we may find that our universe is far more complex and mysterious than we ever imagined, with possibilities that stretch the imagination to its limits. What are your thoughts on whether or not we can ever know what came before the universe? The search for answers continues to inspire curiosity and drive scientific exploration forward. I hope this video does the same for you. If you enjoyed it, consider leaving a like and subscribing to the channel. Thanks for watching.